Log on, tune in, find out. Another good idea from Cambridge.
One talk in this session before lunch. So I'd like to introduce Jesus Lopez Fidalgo from the University of Castilla-La Mancha.
Thank you. Can you hear me? Okay. Well, I want to thank Rosemary and all the organizers for taking their time to organize this and give us the opportunity to spend some time here learning, collaborating, and forgetting about any other duties we have in our places. And then I want to thank also Darius for organizing this workshop and inviting me to be here and to give this talk. This talk is a joint work with Mariano Amo. Is one of my former students. We still work together. And Emilio Porcu, perhaps some of you know him, is from, he's not from the experimental design area, and he's from Italy, and he's now in our university. And well, the problem comes from a real problem. I will tell you about that. Some of you know the problem because even some of you, at least two of you, have been working on this model, as a matter of fact. So let me give you an outline of the talk. First, I will try to justify the model, why we try to modelize the covariances in this way. Then I will give you some theoretical justification of what we are doing, some mathematical justification. Then we will compute optimal designs for two illustrative examples. One of them is a non-real example, but the second one is the real example. So we will apply all these two different models. We will do a sensitivity analysis, very exhaustive, just to show how it works, how is the robustness of the designs against the misspecification of the parameters of the covariance model and so on. So this is the main idea. So let me tell you the story. The story is in our group there is an engineer working in a factory, in a uranium factory. What they do is to produce fuel for the nuclear plants. So they receive the uranium enriched. They have to do the last step in enrichment of the uranium, and then they produce the fuel, the material that goes to the nuclear plants. They produce some pellets, like coins with 3 times thicker or something like that, black, and then they put these pellets on a tube, a long tube, and they assemble several tubes, and they have the element to put it under the water in order to stimulate the nuclear reaction. Okay, this is what they do, and in that factory is very safe, as a matter of fact, because, well, they don't do anything very risky, but they work with uranium, so there is always a risk, and there is always the possibility to have an accident, a leak of radiation, and so they have to be prepared for acting very quickly, and also not only for the safe and the health of the workers, but also to take some advantage of this accident, in the scientific sense. For example, trying to estimate how big was the leak, and at what time was the leak, And well, in particular, in every area, there are areas with more risk than others, of course. And in every area, they have some sample takers, some sensors, some filters to measure a possible leak of radiation. And but the thing is, they only check these filters after each shift. There are 3 shifts every day, every 8 hours. They work a shift, and at the end of one shift, they check the filters and they measure the radiation, and they realize at that moment whether there was a radiation during those 8 hours. So they can check that only at the end, but they don't know exactly the time where this was produced. Once they realize there was an accident and a leak of radiation, they have to take the people to Madrid. This factory is about 200 kilometers from Madrid. And in order to do the bioassays, they have to take the people to Madrid. That is the place where the technology is for this. So they need some time, some kind of 4 hours or something like that, plus the 8 hours of uncertainty. So we will do the first bioassay about half a day after it happens, or at the most. And then what we have to do from the optimal experimental point of view is to tell them what is the second time to do a bioassay to the same worker, and or the third time or the fourth time. But so this is our job here, trying to give them some optimal times to do the bioassays. Okay, so the model of the elimination of the radiation in the human body, in particular the elimination on the lungs or in other compartments of the human body, is modelized, is known, is homologized in the world. The International Radiation Association, or I don't know whether it's an association, an institute, or whatever, they give the model. So the model is standard for all of the countries and everywhere. So we know the model. And but in this case, we have to measure, to do some 2 bioassays to the same person. So there is some correlation between these observations. So we need to consider to model the covariance between the different observations for the same worker. And this is new. This is not standard. This is not done. So we need to think something about that. We have done some work, Bernard Miller and Milan Steldik, some other people from my group. I have been working on this kind of modeling the variances. Usually we consider isotropic covariances, meaning that the covariance depends on the distance, in this case on time, on the difference of time between the first observation and the second observation, and so on. So the model, as a matter of fact, is a large sum of exponential. It's a compartmental model, but it's a very large sum of exponential. This is because we consider many compartments in this case, in the lungs. No, not in the whole body, but in particular on the lungs. So we consider many because, well, this is very well studied, and they know the transfer rate from one compartment to the other, and this is the model. The usual assumption is there is a usual assumption for heteroscedastic models in general, that is to consider the variance as a function of the mean of the model. And so we thought, well, why not considering the covariance also as a function of the mean? It makes some sense. As I told you, the model for the mean is very well known and it's standard, but the model for the covariance is not standard at all. We have to think about how to model that. Okay, so we consider, or we are trying to consider in this work, the covariance, a covariance structure depending on the mean. That is not trivial. It's not so easy. Because for the mean, you can consider any model. There is no restriction about the model. But for the covariance, you need to consider something that is going to be positive definite. You need that. Otherwise, it's not a feasible covariance. And this is the important point in this work. So we need to give some conditions to construct covariance models, covariance functions, to be positive definite. Okay, so we consider a model like this, the observations taken at different points, and there is a correlation between these different points. So we consider epsilon is a Gaussian process with weakly stationary correlated observation. We still preserve the property of isotropy for the covariance, so the covariance still depends just on the difference between the two times, and that's it. But at the same time, we want this covariance to depend on the mean. Okay. Well, if we preserve the property of isotropy, the variance has to be constant. So, well, so the covariance is going to depend on the mean, but the variance is going to be constant. But there is a second step here, and try to do something for more general variances and covariances. So the objective is modeling the covariance structure through the mean through a positive definite function. Okay. So this is the covariance function depending on h. H is the difference between t and s, the different times, the lag. And we want to find functions psi, such that this composition is going to be positive definite. Well, this is the definition of a positive definite function. It's just to produce a covariance matrix that is positive definite. And what we want is to find conditions for this for these two functions, as a matter of fact, for the mean and the psi, in order to have a positive definite covariance structure. Okay. Well, this is the definition of completely monotonic function, because it's crucial for finding the functions psi to give you the covariance structure. And well, you see, the completely monotonic means the function is positive on the positive real line, is decreasing, and it's convex, and so on. Okay, these are the first properties of this function. So it's not very strange. It's something near reality.
Okay, then we will use a couple of theorems. This is one of them. The Bernstein theorem says that a function is completely monotonic, then it is the Laplace transform of a positive and bounded measure mu, something like this. This is very important for the proof of the theorem we are giving for the conditions. Then we will use also the Poljar's type criterion that says that if we have a continuous and convex function such that it values 1 at 0 and is even, and the limit is 0 when t goes to infinity, then there exists a continuous CDF such that the derivative exists, it's even, continuous everywhere, except perhaps at t equals 0, and such that this is the Fourier transform of this measure. Okay. Then, well, I told you two couple of theorems. They are three actually, but the third theorem is Bochner's theorem that says that a function is positive definite if and only if it is the Fourier transform of some non-negative unbounded measure mu. Okay. With these three theorems, we will give some conditions for having positive definite covariance matrices. Well, from these two results, we can say that if psi satisfies the Poljar's conditions, then it is positive definite. That's quite important for the results afterwards. Okay, now, first, the lemma, so for giving you the main result is this. We consider the inverse exponential function and a mean, a model for the mean that is continuous, increasing, and such that the limit when t goes to infinity is infinity. Well, it's not a strong requirement, but it needs to be satisfied. And then the composition has to be convex. As a matter of fact, we will see that the only thing we have to check is that this composition is convex. The only thing we need to check at the end of the day. So I will tell you the whole story. And so then the composition of these two functions, well, normalizing all the function by this, is positive definite. Okay, this is the lemma. I was told to skip the proofs, but let me give you some hints of the proofs. Okay, the composition is non-negative, decreasing, convex, and positive on the real line, and vanishes at infinity. So it satisfies this particular composition. Remember, psi here is just exponential, and the value of phi at 0 is 1. Phi is this function, and we can extend the definition of the model for negative values in the usual way. And so it meets all the requirements of the Poljar times theory criterion. So then the lemma is okay. So now the theorem, that's the main point. The main point is that if psi is completely monotonic function with this condition and eta satisfies the conditions given in lemma, then the composition is a permissible covariance function on R. That's the main thing, and this is all we need to check whether our model is fine or not. Again, the proof, just some hints. Using Bernstein's theorem, this implies that psi is the Laplace transform of a positive unbounded measure, something like this. Okay, if we compose this with the mean, we have this.
So all we need to check is whether this function here is positive definite or not. After that, we know that positive definite functions form a convex cone with the topology of weak convergence. So then this is a kind of limit convex combination of positive definite functions, and then we know that this is positive definite. So, but in the lemma, we prove that this function here, is positive definite. So then we have all the machinery to prove the theorem. So we have that the composition is positive definite for any finite and positive measure. So now the question is, well, but we need a completely monotonic function to modelize this. That's true, but there are quite a few known completely monotonic functions we can use here. We don't need to check whether they are a particular function is completely monotonic or not. We just use the known monotonic, completely monotonic functions. Okay, there are we use the Matern functions that is constructed with the modified Bessel function of the second kind, and this function decreases with the parameter phi, increases for small values of t and decreases after some value of t with respect to the second parameter. By the way, we are not interested in estimating these parameters. I mean, in this work. That might be part of a second or a third step of this. We are interested in estimating the parameters of the mean. Special cases are the exponential model, very well known, and that is the covariance function associated to an Ornstein-Uhlenbeck process, and the Gaussian model for gamma when gamma goes to infinity, and the autoregressive process of the third order is also there. So there are some known, very well known cases considered here under this function. Then we consider also the Dagon function, that is much simpler visually, and here it increases for small values of t and decreases after some value of t with respect to the parameter phi. Well, I told you that in our particular problem, the first biopsy is observed half a day after the accident happens. So as a matter of fact, we are starting not at 0, but at 0.5. Taking into account t it's measured in days. Okay. Then increases with respect to gamma, and then we use the Cauchy function. Cauchy function increases for small values of t and decreases after t equals 1 with respect to phi, and decreases with respect to gamma. Well, just to know the behavior of these functions in order to model correctly the particular problem. Okay, well, these are some plots for some particular values of the parameters of these functions. So we have the Matern is here. I think you can see the colors well. And the Dagon is this one. I cannot see the colors well. But anyway, these are just an example. So now let's go to the optimal design background or context. We will consider exact design because we have correlated observations. So for us, an exact design is a collection of points, and of them may be repeated, but not in our case, because we are considering measurements on the same worker. And the Fisher information matrix is computed as usual, taking into account this is the CDF of the whole model. And then we need to compute the log likelihood, and then the derivatives and so on, and we have the information matrix in this traditional way for the correlated observations structure, where sigma comes from the correlated structure of the observations. Okay. So we have the means, eta, and we have the covariance structure there. Okay, so we are focused on the optimality. We will compute the optimal design, just the optimal design. And we call you the definition of efficiency of a design, and the efficiency is this measure here between 0 and 1, meaning that if the efficiency is 60%, this means we can save 40% of the observations with the optimal design. Okay. Then we have some numerical algorithms to compute optimal designs when we have something like this, a model with correlated observations. We use the Brinkulov algorithm adapted by Lusinski and Atkinson and translated into English, as a matter of fact, because the other paper is in Russian and I don't speak Russian. Okay, so now let me give you the examples. First, we consider this non-real example. This is an example with 2 exponentials, and we have 4 parameters to be estimated. Okay. Now the design space is 0 to 100. I told you it's not real, but we can think about days where the bias is going to be realized. And we use these nominal values. Okay, for these nominal values makes the problem near the real problem. And numerically, we check that the composition of this function is convex on T for the values of these parameters used here. And so we can use the theorem here. We can use the theorem for the functions I showed you. In the computations, the 4th point of the design, we computed 4-point designs, 4-point exact designs. Well, first because we have 4 parameters, we need at least 4 points. Well, not necessarily, but it's good to have at least 4 points for a model like this. And then the 4th point is always in the design. It's always the maximum point of the design space, so 100. 100 is always there, okay, for this particular model. So we consider the Matern function, and then for different values of psi, phi, and gamma, these values in all the cases means that, well, sometimes we have a narrow interval for these values, but sometimes they can be just positive. So what we did was to consider the limits, the limits for the parameters. Also, when there was no limit, we considered the moment when the design was starting to be the same all the time. Okay, usually because the correlation was so low that the problem converges to the non-correlated problem. So this is what we have for Matern. Well, as a matter of fact, all these designs, let me show you this is the design for the non-correlated observation. That is good to have it as reference. As you can see, all these designs coincide, and this here coincides with the with this design, with the design for the independent observation. This is because this area here is the area where the correlation is quite low, so it converges naturally to the design for non-correlated observation. Well, in this particular case, the first point, 0, is also in the design. It's always in the design. Okay. The only change is in the two central points. And then this is the Dagon type case. We consider again different values for the parameters. And in this case, the limit is here. That is, it's not exactly the design for the uncorrelated case, but you can see that it converges from here, coming from here, This is because here we have the less correlated case. Well, increasing the values of gamma is related in this case to increasing the strength of the correlation. Okay, so this is the least correlated case. Then we have the Cauchy case, and here the limit is on the right hand side. And again, because in this case, when you increase gamma and phi, the correlation decreases. Okay, and converges naturally to the optimal design. Okay, well, in this case, the first point, you see, once we decrease the degree of correlation, then the 0 is there. The first point is there. But when you have high correlation, the first point is 1 day later after the event. This is not the real case, but this is the situation here. But what is more interesting is to check what happens when we are wrong choosing the nominal values of the parameters, where we are wrong choosing the wrong values of the psi function, or even when we choose one covariance, the Matern function, but the true one is the Dagon function. So this is what I'm doing now, sensitivity analysis, more or less exhaustive about all this. Okay, first of all, some remarks. As I told you, the maximum point of the interval is there in all of the designs. The two intermediate observations decrease slightly with the correlation, so they go to the origin, and the minimum point of the interval is in the optimal design when the strength of the correlation decreases. These are general remarks about this. And all the designs converge to the optimal design for the uncorrelated case when you decrease the degree of correlation. That is saying nothing. But we checked that the designs, I didn't show you specifically, but we saw that the designs are not very different when you consider the same strength of correlation for all of the different functions we have been using. We use many functions because here There are included 3 times all the combinations of the parameters. So we have been using a lot of them. Okay, now the sensitivity analysis I promise. Well, first of all, if we want to do a sensitivity analysis against the choice of the nominal values of the parameters, we have to choose some values in a neighborhood of the nominal values. How to choose this neighborhood? So this is what we did. We choose 3 points. I will tell you why only 3 points. 3 points for each parameter, and this sigma is estimated with the standard deviation obtained under the initial design. Well, it's the standard deviation of the estimate, not the standard deviation of the parameter properly. But well, it's something. It's something. And so in this case, if we use just 3 points for each parameter, we have 3 to the power of 4 different possibilities for the 4 parameters. Then we have 4 possibilities for phi, 4 possibilities for gamma. So we have around 2,096 different cases. This computationally is unaffordable. It's too much. Well, it can be afforded, but is very time demanding. So this is for the combinations of Matern and Cauchy. And for Dagon, we have only 972 because in that case, one of the parameters cannot be greater than 1. So we consider only 3 possibilities for that. So what we did was to find a fractional orthogonal design of size 9 for each combination of the covariance parameters. And we try with these parameters here. So here the design is used for the sensitivity analysis. It has nothing to do with the model and so on. It's just for the sensitivity analysis. And in this case, we only needed to compute 144 designs for these 2 cases and 81 designs for the Dagon case. Okay. And the results, just summarizing the results. In most of the cases, the relative efficiencies were higher than 95%, meaning that, well, it's quite robust. This model is quite robust against the misspecification of the parameters. Well, there are some, I know there are some criticism about the way we did this, but I think there is always criticism about the way doing the sensitivity analysis. Now, if the misspecification is on the parameters of the covariance structure, what we did here was just for the 4 parameters of the mean, just for the 4 parameters of the mean. Of course, changing the different values of the parameters of the covariance of phi and gamma that we are not estimating. We assume they are known in advance. Okay. So now, if we change, we consider the misspecification of the covariance structure versus these 2 parameters, gamma and phi, then we see that for the Matern covariance structure, there are a few cases with less than 50% efficiency, meaning that we have to be very careful with the choice of the gamma and phi. That is sensible because this means changing phi and gamma, we have different strengths of correlation. So it makes sense that we have to be very careful with that. Okay. For Dagon it's a bit better. The efficiencies are in most of the cases, or all of the cases, more than 88%. That is quite good, meaning that perhaps this perhaps no, this model is more robust than the Mater model. And for Cauchy, well, if we consider the state of nature, so these are the true values of the parameters, and we consider these values here. So if the reality is that there is a strong correlation, but we consider no correlation or almost no correlation, then the relative efficiency is around 82%. That is not so bad. If we consider the opposite, we assume the state of nature, the reality, the true correlation is very low, and we find the signs for that strong correlation, then the efficiency lows down very much. Okay, now we consider the third study. So the first was against versus the parameters of the mill. The second was versus the parameters of the covariance, and now we consider what happens if we choose Matern and the true one or the best one is Dagon. Okay. Things like that. So after doing this, we observe that Cauchy covariance ensures the higher levels of robustness. So it seems Cauchy is much more robust than the rest of the models. Well, in this case, for Dagon covariance, so if the true covariance was Dagon, then the efficiency was 90%. In this case, is only in the extreme case, assuming a double source of misspecification. So if we change the model, for example, we consider that Cauchy, the model of Cauchy, and the real model is Dagon, but we consider Cauchy with a strong correlation and Dagon with a low correlation, then the efficiency lows down. That is also logic. And analogous considerations for Dagon and Mater covariances. And so this is the real case. The real case, in the real case, we have well, for the real case, we have considered previously to this work exponential and triangular structures independent on the mean. Just structures for an isotropic covariance, but independent on the mean. And now we are using this. This is the model. We have here about 68 summands of exponentials. And well, first, this makes sense from a practical point of view because each gamma, alpha, and beta here has a meaning. Okay, they have a meaning, a physical meaning. But of course, from the mathematical point of view, we don't need to use all the summands. As a matter of fact, in practice, gamma, alpha, and beta are known because they are given by the general instructions or of the Radiological International Institute. So the parameters here are R, that is the magnitude of the leak, the magnitude of the accident, and P, that is the size of the particle. Of course, the elimination is different. The elimination from the human body is different if you have small particles or big particles. Okay. And T is the time where we have to check to do the biopsy. And they are very interested in practice in estimating the value of R. Remember, we start at 0.5. The accident was at 0. Well, of course, we have been using, in other works, we have been using the possibility to introduce here in the model, or better saying in the optimal criterion, the uncertainty of the time of the accident between those 8 hours. Remember, we know that the accident happens in the last 8 hours, but we don't know the exact moment. We can use also some distribution, some probability distribution for that time. For example, a non-informatic distribution like the uniform distribution. We haven't used that here in this work in particular. Okay, so reduce R is the quantity of absorbed radiation in the moment of the accident. P is the magnitude, the size of the particles, as a matter of fact. And we use these nominal values for R and P. Because, well, we can say that this is a significant accident, and the size of the particles are of this nature. Okay, so we need to reparameterize the model because this model is decreasing, and in order to apply the theorem, we need an increasing model. Okay. Just for the covariance, so the model is still the same, but the covariance has to depend now on this, not on the original model because it's decreasing, but on this new model. Okay. For computational reasons, we use just 4 summands. It's very well known that we don't need to use so many exponentials for the model. This works perfectly, equally well than the other one. We adjusted this model to the other one. And so we numerically check the conditions of the theorem. Frequently it's not possible to check them analytically, so we have to check it numerically. And so these are the designs. 2-point design. We have only 2 parameters here. We use only 2-point designs. If the correlation is low, then the first point is always there. But if the correlation is there, then if there is a strong correlation, then the first point moves a little bit upward. Well, for the Dagon case, we have this situation, well, with the same comments, and for the Matern case, we have these designs. Some remarks that is more interesting than seeing the particular numbers. When the strength of the correlation decreases, in all the cases, the optimal design converges to this. Well, this is the first point should be there, but because we use this transformation of the model, then we have results like this. Why I'm saying that the first point should be there? Because for the uncorrelated case is there always, and well, this doesn't mean that it has to be necessarily for the correlated case, but also for the correlated cases we have been using non-depending on the mean, we have found that the first point is always there. And the optimal design is characterized by the presence of the first point, and the other points move in a neighborhood of 70 days, about 70 days. So the second biostate has to be made about 70 days after the accident. This is for the statistical goodness, not for the health of the worker, of course, but we can consider that as well. Major strength of the correlation is related to the major distance between the points of the designs, of course, and the sensitivity analysis says that all the designs are robust with respect to the nominal values of the parameter p. So if parameter p is fine, the specification induced by the covariance structure is around 85% when the strength of the correlation is similar. This is related to the values of phi and gamma. That is the different correlation structures, strength and structure. Very low efficiency is obtained if the specification source is high in terms of strength of the correlation. I think we saw something similar for the other case. And designs with no contiguous points exhibit higher efficiency. That's remarkable, about 80%. Possible explanation is the presence of the minimum point in the design. Some general comments. Well, now we are thinking in doing something when we consider the variance also depending on the mean, not only the covariance. I told you at the beginning that the covariance depends on the magnitude of the mean, but the variance is constant because we consider an isotropic covariance. But now it would be very interesting to consider a non-isotropic covariance structure in order to have also the variance depending on the mean, for example. And this means the process is not stationary anymore. The theorem we gave you is not true if psi is only convex instead of completely monotonic. So if some of you thought that perhaps relaxing the conditions and just asking psi to be convex is not enough to, well, this is the countersample. And that's it. This is all. Thank you very much for your attention.
May some comment. Your lecture gives a good example for functional approach, since here we have design on interval, the number of points is fixed, and certainly the model will be a real function, a real analytic function. So the dependence of design point on the parameters is real analytic functions.
Yeah.
And also the monotonial properties can be proved strictly analytically, since the structure of equilibrimetrics is okay.
Okay, yeah.
We
Yeah, we
continue.
will talk about that. Thank you.
When you mentioned at the beginning that you wanted some covariance that depends on the mean, I thought that the covariance between the 2 points would depend on the mean at the 2 points. But
Right.
what you have, in fact, is a mean evaluated as the distance between the 2 points.
Yeah,
So
right.
what does
Right.
it mean? I mean, it's difficult to feel what the meaning of that.
Yeah, I know what you mean. We have thought a lot about that. Of course, it makes sense that the covariance is not only depending on the distance of the points, but also on the mean somehow. And I told you this is a first step, perhaps the simplest one, to find some properties now for a covariance depending on the means for the 2 observed values. But this is a first step. And you asked for the practical interpretation of this. Well, it has made some sense if you consider somehow that the distance between the points, um, mm, somehow the covariance may depend on the mean for this distance. But we have to check in practice, so it's not, I agree, it's not completely justified from a practical point of view. So as a matter of fact, what we are doing now is to try to find conditions for that function to be positive definite when the covariance depends on the mean at that point, and also the covariance depends on the two means, the mean at one point and the mean another point. So then the process is not non-stationary anymore. Yeah.
Let me follow up with that. The other thing, you have to remember covariance is only a pairwise dependency.
Yes.
So it's only for 2 points. And therefore you make the h was a constant through the way. But if dependence came from three-way or something, this probably need to modify a little bit. Careful.
Yeah, well, we can introduce some covariate or something to tackle this problem.
Now if I understand what you have here over the same question is, you have time s and time t, and you call it h, I suppose.
Yeah.
And that covariance is, but maybe it's only pairwise, only 2 points. The time may be through. That's
Well, but we always consider all pairwise possibilities.
right. And
Do you have 4 points?
that's a good point, but that's also the limitation.
Yeah.
Only pairwise. If we got 3 points, S, T, and W,
Yes.
whatever, the 3-point dependency, apparently model cannot handle that somehow. Is that-
But I believe this is included here. Is if you are not considered some third variable giving some, I think it's included here. What do you
Now, there's some discussion of this beginning in what you might call the computer experiments community, and they want they describe it like this: they want somehow for the covariance function to adapt spatially, so it's non-stationary. So one suggestion is that you use some of the tricks from finance, where you take a local space dilation, and that space dilation basically changes the metric locally, and then basically you're creating a Riemannian manifold by distorting the space locally, and then allowing it to adapt in some ways. And there's quite a big literature connecting this kind of metric embedding theory with your functions. The two missing names in your talk, one was Bernstein, but not the Bernstein theorem, Bernstein functions, where you have these big catalogs of Bernstein functions. Each of which gives a covariance curve. And then the other name is Schoenberg, who did the embedding theory into Hilbert space, basically. So there's a big body of mathematics. If you're going to do this properly, so it's the sort of maths one needs to learn to do the dilation, the local dilation. It's a complicated story, but I can give you. I'm writing a paper on it, so you can.
Okay, thank you.
I'm not sure I follow everything, but
No
is there
space.
here something special about the problem that you're dealing with? After all, we know that radioactive decay is exponential, and it's exponential probably in every part of the lung, wherever compartment you pick it. So you can take any compartment and you will have the same
Exponential.
behavior. If you want to identify decay, any compartment is as good as any other.
Yeah.
And then the third, final thing is that after all, we are trying to estimate here some very complex, both maybe two parameters, but also the covariance structure with only 2 measurements. Isn't this a tall order?
Yeah, okay. Well, you choose just 2 because this is the minimum we need for
even
2
three-
parameters model.
even three
But
would
of
be-
course,
four
no,
would be
we have done it as a matter of fact in previous works. So it's not. It's just an example. Okay.
Is there something special about the problem here that we know, there's a monotonic decay because physics says it is, and then you can take advantage of that, or not? Am I missing something?
Yeah, I think so. Yeah.
I just want to comment on this. So, if you have a correlated model, then not always information increase with adding other observations. So you don't have just a classical compartmental model fitting to the system of linear differential equations, but you have also the information on the transition Markov probability through the covariance. So your process can be very fine with 2 observations. I mean, we have proven in the paper by test. I can send to you. And regarding the second comment, again coming to the point, if you have a feeling that you know something of Markovian transition, that means that in a way that you can connect the first and second moment, it can be very different. If you consider the Gaussian process just on the first and second moment to be independent, it's a very different issue.
Well, one last.
Sort of a follow-on question, but more about the science of it. Can you say something about the characteristics of the measurements that you get? Are they breadth or tissue samples, or are they an array of tissue samples? Are they scalars that you get from the subjects?
I'm not sure.
Okay.
I don't know about the details of that.
But somehow they have a model for different compartments in the lungs.
Yeah.
But
There is a big set of differential equations given the final model, the linear differential equation, but a lot.
Okay, so one last.
Again, I mean, the model has 2 parameters: the amount of release, and then p, which is the size of the particle. I mean, is there just one size of the particle, or would you expect a population balance on the particles?
Well, it's the parameter, so we need to estimate the parameter.
Yeah, but in reality, is there one particle with a given size, or is it just an approximation to something which is rather more complex? And is the sensitivity to that assumption or the order of magnitude of the others?
Well, we did the sensitivity analysis for the p parameters, assuming different values near 5, because we know, or they know, the value of the size of the particles are around 6. So we use that for the sensitivity analysis.
Okay, well, we'll draw it to a close there. So it's lunch now, and the next talk's at 2 o'clock. So I'll just thank the speaker again.